Thank you. Well, first of all, thank the organizers for inviting me. It's really a big pleasure and a big honor to participate in this conference. I will review some of the work of Brouwer, and myself, and actually the whole kids' collaboration on our work on testing gravity models with declensing. I also will show some results of our Fornax cluster survey in dwarf galaxies, which is work done with linear Pelletier and our PhD Sarah Eftekhari. So let me start, but since we are at the MOND40, let's take the liberty to step back even 10 years more to the 70s, where a lot of things happened in radio astronomy. And I start with this epic picture, which is Professor Oort giving his lecture at the old observatory in Leiden, Sterrenwacht, Leiden, 1973. This is the last lecture in the old building. For those who don't know Professor Oort, he was actually the founder of the Western Radio Telescope, so he's actually the founder of this cloud. And where all the H1 observations were done on the flat rotation curves. And he was actually also the founder of the European Southern Observatory. So what is noticeable in this picture is that the whole room was filled with radio astronomers. And actually I'm on the right side as a very young student, and I'm proud to be there as a part of this enormous crowd of radio astronomers. Actually Leiden was the mecca of radio astronomy. All the radio astronomers came all over the world to visit Leiden and to work on it. In Leiden actually we concentrated mostly on continuum observations. And while in Groningen, a lot of work has been done on the H1. And clearly that has led to Bob Sanders being involved in this program. Alan Bosma was actually the first to map flat rotation curves in the spiral galaxy. So I did my thesis in 1978, doing 610 gigahertz observations of the Hercules cluster and also the Cluster. And actually in those days it was really raining discoveries, one after the other. And it was really a fantastic time. This is the cover of my thesis, and you see the isophones of galaxy counts from Zwicky, this Wiki catalog. And actually people like Tift and Terangli were very keen on measuring the redshifts of our active galactic nuclei, which we're detecting in the radio. So we were the first to get all these redshifts for the galaxies in these clusters. And we then discovered that the redshifts were more or less identical. In other words, this stuff here is really forming a super, a supercluster. So in passing we discovered superclusters and large-scale structure in the universe. At the same time, George Murray detected this radio source 129 with a very long radio tail. And the only way we could understand this very long radio tail is by assuming a thermal confinement of the radio block by a hot intergalactic medium. And we proposed, George Murray proposed, this hot intergalactic medium should have a density of the order of 10 to the minus 3, pretty high. And I can tell you later on this has been confirmed by X-ray observation. Actually, I proposed that these were the X-ray error bars of the Uhuru and Ariel 5 satellite, and I proposed that this giant, supergiant galaxy there is most likely the source of a halo of X-ray, and we found about 14 of them more in our surveys. And we proposed them to the Einstein satellite to put them on their observing program. And actually the Einstein satellite did detect all of them. And this is actually the main core of the large number of detections of giant ellipticals and CD galaxies, which have been published by Christine Jones and Bill Forman. So it was really a very exciting time. Most important thing for this talk here is I will talk my way that this narrative of the 610 gigahertz observations and the narrative of the H1 observations will join somewhere in the middle of my talk. But one of the long-lasting discoveries is this head-tail radio sources here at the outskirts of the supercluster. again, applying the term confinement to the radio blocks here, we found that there must be a medium, intergalactic medium of density of the order of 10 to the minus 5. So, an order of magnitude 1 or 2 or magnitudes lower. Until today, this gas has not been detected directly yet with X-ray observation. So these are the first hints of a supercrystalline medium with a relatively about 10 to the minus 5 density. Same time, we derived the velocity functions for X-ray sources. Einstein did detect all the ellipticals and giant ellipticals, didn't detect any spirals, and we detected the first velocity function of elliptical galaxies. Right, so this is my little video. Then we go to the VAR. Of course, I don't have to explain to you what a VAR is. Since it's a very useful way to represent the data, it's a great idea. And I will use the VAR also in my presentation. You all know now that on the horizontal axis we plot the baryonic matter based on the stars and observation of the stellar mass, assuming a mass to line ratio, adding the gas. While on the vertical axis we plotted the numerical mass. Well, the VAR has a few very good things. One is that you can get closer to physics by going to accelerations, so that's very good. Secondly, it allows you to combine data from different sources, from different observations. So I will combine between the virialized systems and rotational systems in Europe. So that's a very nice property of the VAR. One drawback is it's a little bit less clear how selection effects work and how errors behave, because sometimes it's not completely intuitive how it works in this presentation. Right, well, you have seen this picture already many times during this conference. They are as defined by Stacy, as observed by Stacy McCook and his colleagues. The fit there is an empirical fit, as stated by the authors, with a characteristic value of 1.2 10 to the minus 10. And we use that fit in our comparison of our weak lensing models with the MOND. For EG, the story is a little bit different, a little bit more complex. The bottom line is that Verlinde predicted a characteristic velocity, characteristic acceleration of CH106. And we use that value for our models. Let me make a little sidetrack. We heard a lot of complex analytical and theoretical considerations. Let me explain that I do for popular public, but forgive me to do it this way also to you people. I explain now EG in a very simple word. In his 2010 paper, Eric proposed a surface area law to explain gravity. And he equated the surface area in terms of the surface area of a sphere in terms of squared Planck length. In his 2015 paper, he equated the effect of dark energy and dark matter in terms of a volume law, with the volume of the universe, or actually the volume of the dark energy, in terms of cubic Planck length. So the two laws, cubic Planck length and the square Planck length. And actually the stress between these two laws is causing the value of CH106. And you can make it very simple, and you can say, well, it's for the same reason that an elephant has a very sensitive skin, dark matter emerges in this theory. So, I should make one note, right? I use the term prediction, and Erik claims very clearly that he also looked at non-event phrasing this theory. So it is a prediction with a big star because he knew what to predict. So we have to be careful, and actually this whole business of comparing observations and analyzing observations, we always have to be extremely careful to not have an opinion before you see the data. I can tell you that in the kids survey, where we do a lot of cosmological tests, most of the tests we do blind. Right? So all the calculations are first done and then at the end we unfold the result, which is done by the person. And on the CDM, well, I don't have to explain you all this is circumstantial. There's nothing fundamental on the CDM that predicts this kind of relation. All right, so this is my humble introduction to lensing. First, strong lensing, just as an appetizer. Well, you have seen probably this beautiful picture of the Hubble telescope, where a remote galaxy, the light of a remote galaxy passes along a bright galaxy in the center. They are aligned. We call the bright center in the galaxy in front of the lens. And you see the beautiful arcs, I think you see them, of the strong lensing of the remote galaxies along the line of sight to the bright galaxy. Now, weak lensing is a completely different business and is much more complicated. The light of remote galaxies passes along the halos of the galaxy, of the lens galaxy, and the image of the remote galaxy, the distant galaxy, is deformed by tangential shear by an order of 1%. That's a very small value. We have no clue even what is the original shape of this galaxy. So the only way to get a feel of what this effect is, what is the effect of gravity on this big lensing, is by doing very large statistics. Great number statistics, as much as you can possibly get. Actually, this is what made us experts in big data. Are you ready? All right, so what we do is we stack the signal of the lensing in concentric circles, go again, in concentric circles around a target, and stack the signal and derive a radiograph of the so-called excess surface density, so the gradient of mass in that circle, as function of radius along the centered on the target. So in weak lensing, we measure the excess surface density on mass. It's big work. It's incredible amount of work actually to do this, and it involves doing very large surveys, deep surveys. It involves to measure redshifts for all these galaxies. So we try to get as much spectroscopic redshifts as we can, but we add photometric redshifts. It requires very high quality observations. It is very good seeing, very good point spread function, as we call it. For kids, we use only data with a seeing better than 0.67 arcseconds in parallel, and in Chile. And for Euclid, the satellite will come up in a moment, we expect a point spread function of 0.2 arcseconds to this work. So there's a lot about this point spread function. This is really very complex. It's not as simple as it was 20 years ago. A lot of effects. If you want to do this very high accuracy measurement, you have to take care of the atmosphere, you have to take care of the focal plane geometry, you have to take care of the color term. That is true for Euclid. The galaxies have a color, and they all have a different color, and there's a color term in the instrument, and so in effect every galaxy will have its own point spread function because of its color. There's probably Brouwer effects in the filters. There's jitter of the telescope, and there's also detected electrons. And I only mention now those points which are related to point spread function. There are many more. And this was actually the reason that we built the Astronomical information system, a complete new system, because we knew this started in 2000 actually. And we built this system because we knew we were going to handle enormous amount of data. It was in the time that we had the Omega pixel on your telephone already a lot. And we had to, we built a new system where we maintained all causality between all the different data items. And I'm not going to elaborate on that, but this system has been used for the analysis of the weak lensing, and actually the same system is now going to be recycled, and has been recycled for the Euclid satellite, and we're going to use it there as well. Just to give you a little bit of flavor of, what is behind all this few graphs I will show you in a minute. While we were building all this very complex information systems, at the same time we were dealing with theories of gravity, which is based on the holographic principle, I got the notion of there's an information universe out there and there's an information universe down here in our computers. And I started organizing a series of conferences in my planetarium in Groningen. And I'm proud to show you the lineup we had in the last summer. We get people from different disciplines discussing these matters. All this is on Information Universe YouTube channel, which is actually now back to the work on the lensing. We use the OmegaCAM camera, which we built ourselves. We started in 2000 with this, and the thing was heavily delayed. We could only start observing in 2012, and all the observations were done 2 years ago, and the kids' final data release has just been published a few months ago. It's, well, we use 1,000 square degrees of the 1,500 square degrees of kits for our paper. Paper is Brouwer. I mentioned them again because we did an enormous amount of work. And the first thing we did is for testing modified gravity, EG, and on the CM, we selected isolated galaxies. And our isolation criterion was no other galaxy within 3 megaparsec with a mass brighter than 10% of the length. That was a very strict criterion. Second criterion was that the stellar mass of the lens should be less than 10 to 11, so to avoid bright central cluster galaxies. We measured the excess surface density in a radio range of 30 kiloparsec to 3 megaparsec. And I should re-emphasize again and again, this is our enormous distances. We are very far away from the galaxies, and in many evaluations, we can use a point source model for understanding the observation. I pass the overall ratio stories, but I go to the, since I see I want to use a lot of time. In the end, we ended up with a sample of 259,000 galaxies for which we measured the mass. Well, this is the picture of the press release, and you see the upwide, the well-known results from the spirals, and this is the result from the weak lensing. I plotted this on top of M87 to remind everybody who looks at this, you know, this is a very deep image of M87, how far away we are from the galaxies in this measurement. Well, you can see the arc is actually been extended by 2 orders of magnitude. It blindly maps directly to the bar defined by the spirals. It follows the square root G of G bar relation. And yeah, well, we have 2 completely complementary techniques, right? 8-long radio, weak lensing, which actually show the same relation. There's a first notion here is that, you know, the error bar is extremely small. And by now, one can state that we know the distribution of the dark matter better than that of the baryonic matter. So our biggest problem in the interpretation is understanding the baryonic matter. The error bar here on the top left, the error bar here, the error bar here, the shaded errors here, represent the systematic errors, which is the uncertainty in the adopted master light ratio. So the adopted master light ratio is probably is even a larger error than this sampling error of our light. All right, then one of the what you might notice here is that it's a little bit above, right? And it's within the I mean it's not within the errors. So one of the first things we did is to split the sample in 2 parts. And we used the Sussex index on the left picture, Sussex index 2, and the color index to discriminate between the early types and the late types. And you can see when you do that for this sample, there's a major difference between the two samples. There's a major difference in the R of spiral galaxies and that of elliptical galaxies. It's at least a factor of 1.5. The 5.7 sigma, which is actually quoted in our paper, refers to this one here. On the right one, we could not even get a sigma because it's out of scale. It's very, in that respect, it's a very significant result. It's also notable that this result is also obtained in this regime, where we're pretty sure that our photometric redshift and redshift are okay. We shaded the left part of the diagram to, as a warning sign, you know, we use photometric redshifts, and at larger distances they can be more uncertain. So it's about, it is a warning sign, you know, we have to be a little bit more careful in this interpretation of this part of the regime, but in this part of the regime, we are pretty confident we do the right thing. And also there, you can see the difference. Well, to explain the difference, you need a difference of an M over L, adopted M over L, master light ratio of a star of 0.4x, which is huge. And so, you know, we have a little bit of problem to explain this observation, this moment, always easy. Then I go back to my introduction, since I have this history in X-ray observations. And when we did this, I remembered, you know, what I did in Matthias. You don't forget those things. And I remember that we detecting the elliptical galaxies all over the place, but no spirals. And I just started to look up the literature and what has evolved. I mean, how has this subject evolved in all those years? Well, the bad news is that it has hardly been evolved. It's rather surprising. This is actually the very best sample, or at least what I can find, on X-ray mass on hot circumgalactic matter. I should have used that term earlier. The hot circumgalactic mass around early type galaxies determined by the Fundamental observation. Well, you see there is a scale, there's a scaling relation. It's not so easy to find, you know, to make a conclusive statement out of this. What we did is that, well, if we look at our galaxies here, which are this mass range, on the elliptical galaxies, we expect that the X-ray circumgalactic matter would be in this range of their diagram, which translates, it's a little difficult diagram to translate to a stellar mass to X-ray mass of 0.121. That's this in 5 times the effective value. Since we go extremely far out, if you transpose to a much larger radii, you have to multiply this number by a factor of 3. So this best X-ray observations we have at this moment predicted, you know, that you could expect an X-ray circumgalactic galaxy of the order of 1 to 3. So what I did, just as a postulate, you know, let's postulate that this is the case. And then I get this result. If I suppose that the galaxies we observe in the kits have a circumgalactic gas of the order of the stellar mass, and 0 for the late type galaxies, then the whole difference is gone. So I think I've said already most of the things I wanted to say in this tape. Clearly, again, you know, the uncertainty in the amount of the circumgalactic matters, gas, is still going to be a trap for all our observations in nuclear and in the future. That's simply because the surface brightness of X-rays at a temperature lower than 77K is so low that we cannot detect. Sometimes it's good to be in line to remind each other. We see all these beautiful things, but there are a lot of things we don't see. And one of them is the circumgalactic gas. This temperature is lower than 10⁶K. The other thing I should mention, I meant to mention, do it now, that we are still completely blind to molecular hydrogen. Molecular hydrogen with temperatures below 100K we cannot detect, although we know that at least there is as much as elemental hydrogen. And it could equally be much higher in certain temperatures. Anyway, This is a technical slide where we put our uncertainties together for those who want to discuss uncertainties. The interesting thing is that we also put the gamma data here. The gamma data is a survey where we have spectroscopic redshifts. So it's a smaller sample, it's open 80 square degrees instead of 2000. And you see that the gamma data is the blue points match to the black points, which is the set with a lot of photometric redshifts. So that gives us some confidence that we do things right. The other thing is you can just compute the dispersion of the individual measurements, because the individual measurements are independent of each other. And if you compute the standard deviation of individual measurements, we get for the kids 1000 survey, we get a number of 0.7 dex, and for the gamma 0.16. So that number, the individual dispersion of the data, matches actually very well to our air boxes. Our air bars are actually even a little bit too large. And it also matches to the scaling of gamma, and the kids survey, the scaling is also perfectly matched. So that gives us confidence that we're doing things right. We have also, of course, to account for systematic errors, and the most dominant one is the MOVL, as I just mentioned, which is this one here, the 0.2 depth. And there is also a smaller systematic error, which has been elaborated by Oman, and we could easily give a whole keynote on this, his measurements on the cosmic simulations, and measuring the RAR in cosmic simulations. He came to the conclusion that in the domain of what we observed here, the systematic error in the RAR, because of the mass model you always adopt, is implicit, is of the order of 0.05. So I think we're doing fine. Also the isolation criterion is confirmed by the gamma data, and that is very strong. But then, ladies and gentlemen, there is breaking news. And that is this one. And this is actually the first time I present this on the international floor. This is actually data from Rosita, and we have been hoping and wishing that this data would come. And they have Rosita's Nature telescope, and they have stacked the signal of 35,000 galaxies. And actually these are the same galaxies which are in our survey. This is the gamma sample. They had a completely different scientific objective in mind. They were splitting the sample in quiescent galaxies and star-forming galaxies. They didn't discuss any cosmology or gravity or whatever. But this is their result. And the result is that they find that the early type galaxies of this overall, it's a stacked signal, are at least a factor 2 brighter than the late type galaxies. As you can see, it propagates all the way. So this is really, I hope, good news also for MOND and EG, because this notable difference in the RAR of early types and late types can be explained with certain galactic matter, and there is now for the first time an indication or a measurement from X-rays of this very low surface brightness galaxy, or surface brightness X-rays, that this is really there. To be added, I didn't say that yet, but clearly this is also matching to the missing baryonic matter. So we solve a lot of things. This should solve a lot of items in the center. Right, then there's one slide. Where am I in time? Okay. There's one slide on the enormous amount of work which Oman did on measuring the RAR in simulations. And I will be quick about this one because I want more things I want to tell. He measured the RAR in the Bahama simulations, which is this graph here, this big error bar, and you see it's a little bit off. And of course, he says, well, I can get it right if I change the stellar mass to stellar halo ratios, can be made right. And of course, the shape is on it. The mice observations, for which we also determined the RAR, are this one here, and the red shaded area represents the areas in photometric individuals, and actually it does very well. But this is very nice, this is good, so let's say the M is able to produce the art, that is a statement one can make. On the other hand, one should note that these simulations are tuned, and they are tuned to the observations all the way. They use the color distributions, they use the velocity functions, they actually tune their simulations to the observed universe. These are not simulations from radio. And that makes it very tricky, particularly because in the hydrodynamical simulations there are two very strong nonlinear effects, which is feedback and ionization. Very difficult to model, so the best way is to tune the parameters and get things right. And I talked to Joe, which is the chief of the Eagle simulation, and he assured me, yes, that is what we do. Never draw any cosmological conclusions from this kind of work. We only say we do this and then we get this. And this, you cannot use these simulations as a test, honestly. That's maybe the reason why you could spend more than 5 minutes on this now. So that's my conclusion. I'm sure Kyle would say something different, but this is how I look at it. Then I would like to spend 5 minutes on the dwarf audience, because as it's clear now that on the big lensing we have not been able to make any discrimination between MOND and EG. So that's a little bit frustrating if you want to test most of it. Now it's important to note there's one big difference between MOND and EG, and that is EG, the prediction is for the mass, excess mass density and the mass within the saturated. There's this term here. This is the mass gradient, which is not in MOND. So this is a prior which could discriminate between MOND and EG. And I know that several colleagues have been looking for this. This could emerge in dwarf galaxies. Low accelerations, this term can show up. That has been done here. I think that is the result. And the result of this term is that at low accelerations, the dwarfs will appear a little bit above the standard deviation. Well, you can see the error bars are very big, and there's a good reason that they're very big, because it's nearly impossible to do this. We contemplated to go to the ELT and do a MUSE dedicated program, and then the computers we need 3 months of observations, and then the program committee will say, no, you can't do this because the spectral resolution of the MUSE instrument is not good enough. So simply, we are not in a good, well, maybe someone knows a better way, but our view is that it's unfortunately impossible to do this. So then we are a little bit in trouble. People are focusing on single colors and single objects, exotic objects, and well, then of course there's always the problem of inclination correction. There's the problem of whether they are dynamical stable or not, which we know they're often not, and there's also the problem of pool molecular energy. So that's also another way to go. So then I worked with Rini and Pelletier on the Fornax cluster survey, and we identified 26 dwarf spheroidals, which are brighter than the dwarfs which Larry has observed in the plot. We had 7 hours per field, and we did integral field spectroscopy, and we could, this is actually a very important problem. We measured the velocity dispersion, say in a handful point at various radius for these 36 dwarfs. And what you can see is that the velocity dispersion is a flat line. In other words, these galaxies are realized, so we are now pretty sure that we have a sound sample of realized object which could be useful for our experiment. Then here are the galaxies, and then go straight away to the RAR of these 36 dwarfs in Fornax. And as you can see, they follow the RAR pretty well, but 3 outliers out of 36. I don't think it's statistically significant. So in fact, these dwarf galaxies do follow the RAR pretty well. That's good. That's nice. But what is the main message here? Well, there are two messages actually in this sample. Because in the same paper we also plot the fundamental plane. And often it's said, right, the dwarf galaxies have much higher, much more dark matter than lighter galaxies. How can it be in the MOND and in EG? And actually what you can see here is we show that they match the bar, but we also show that these dwarf galaxies follow the straight. So there are galaxies, these galaxies follow the fundamental plane. Or there are theoretical considerations why you think this should be the case, but it is very nice that it is observed. So actually, this solves the riddle of high dark matter in dwarf galaxies in context of MOND and EG. So, well, I plot all this stuff in one graph. It's a little bit ugly, but it's all there. The Fornax, the spirals, and the weak landing. There are a few notions now. I think the result of the dwarf galaxies is more than just casual. It has something to say, because these dwarf galaxies have a typical scale of 0.6 to 1 kiloparsec. And the RAR is observed on the same scale as the same RAR has been observed in the spirals with a 50 to 100 kiloparsec scale. So we get the same relation, and of course, I like it, but we get the same relation, we observe the same relation with a factor of 100 different scales at the same acceleration. And that is clearly something which is, I find that a very strong point. And it would be extremely difficult to assemble this by circumstantial effects in the machine. So that is actually my main conclusion when I plot the data of the Fornax dwarf modules in this diagram. That the scale invariant of the RAR, I prefer to call it scale invariant rather than rho. That the RAR is a scale invariant, and clearly the Fornax dwarfs make the case. Now, yeah, we really, you really want to discriminate between EG and MOND. Clearly, it could be done on the basis of the Sursik index, right? All the samples. We try to do that, but it is really extremely difficult, because if you use the Sursik index not on a log-to-log scale, you see that all these gradients all over the place. And if you stack signal with different galaxies with all the different gradients, I think you will be lost. Maybe there's a bad person here in the audience. I invite you to spend 2 years of your life to do this, but there is a possibility that we can get this out of the weak lensing data. And then to get the DM, the arctic, as a prior. Let's see whether it works or not. Would be an ultimate test. The other ultimate test is actually where we built Euclid for. To be honest, we started already building Euclid in 2009, even before we started observing with OmegaCAM. It's quite strange. We are now really ready for Euclid. And the most important thing there is, for Euclid, it is really designed to do all this as function of redshift, out of the redshift of 0.2. And up to the redshift of 2. And so this is the main science case for Euclid. Cosmology, there's of course also the sigma 8 omega matter tension, which is clearly also a objective for Euclid, large scale cosmology. But Euclid is going to be able to discriminate these models, provided we have the models. So this is one of the things I would call upon. We really have to make models also for MOND, which we can predict what Euclid would see, rather than making it work after the fact. So that's and so I talked to Erik a little bit and said, oh, Erik presented this on the last Information Universe conference. This is a first very well, I don't dare to call the back of the envelope model, but you had a lot of disclaimers. This is just the first attempt of Erik to do this. So but this is a graph of the predicted ratio between the dark energy, effective dark matter energy compared to the CDM, which actually has a strong radius between 0 and 2. So, not going to do details yet, but that's really what we are after in the Euclid experiment. But the good news is 5 minutes, thank you. The Euclid experiment is, there's good news that Euclid is going to be launched. It's not formal product yet, but I can say it here in this room that the launch will be in the 1st of July. Cape Canaveral was a SpaceX rocket. You're ready for it. It will measure 2 billion, it will measure 2 billion galaxies, near infrared spectra of about 35 million. It will survey the extragalactic sky with an unprecedented amount of data. On the left side here, there's the Hubble Deep Field, which took about 250 days. On the right side, this is what Euclid will do in 4,400 seconds. Not as deep as Hubble, but we still get 300,000 galaxies in every observation of somewhat more than an hour. So we will map the whole sky, extragalactic sky, which is about 1,500 square degrees. We avoid the galactic plane, we avoid the ecliptic plane, and there's still 1,500 square degrees of sky is left over. And we will map that, and we do exactly the same job, well, the same kind of things which we have been doing as kids in OmegaCAM. But then as function of redshift. So there's a lot of work in getting the redshifts right in Euclid. It will take about 5.5 years to acquire this data, but the first data releases are expected in November. And the first scientific evaluations are expected in a year from now. All right, so I will take I made a little Excel sheet, an Excel sheet. Of my conclusions. And I thought, well, since I started with the art school, and clearly art was also one of the people who was on the finance school. I remember then this BBC interview with Feynman, get many BBC interviews. But one of these interviews he was asked a question, what are the criteria to accept a hypothesis? And he answered, of course, good physics and good mathematics. Predictions, and the last one I made a lot of impact on me is that you must also have an avalanche of small things which become understandable. And this is clear with observations. So this is the Excel sheet, this is my last sheet, Mr. Chair. I will go through it very quickly. First of all, my opinion is the jury is still out. So before everyone dies on me. The jury is still out. I think we are not conclusive yet. We have learned what we want to do with Euclid. I don't have to elaborate on the physics of MOND. In EG, I already told you the basic principles. We should realize that in EG, acceleration has a temperature, and also that this is an extremely heroic theory. Because in the end, it explains dark matter, dark energy, and quantum mechanics, GR purification in one go. So one could also look at EG as a class of models, and there could be more instantiation. Well, in CDM there is nothing fundamental; it's only circumstantial. In terms of free parameters. Well, the empirical value of MOND is probably 1. If the AST effect is leading to another parameter which probably also don't like, then it will be 2. In EG there is a 0 free parameter, but there is a big star on it, as I already said, because you knew what to predict. In CDM there are lots of free parameters to do the job, and at least 2 of them only here affect the system anymore. The scale invariance of the dwarfs I just mentioned, which is positive for MOND and EG. The scale invariance of the bar presented by Stacy is also the very small error bar. I remember where you are. There you are. Now, the first time we looked at it in Napoli, the first surprise was the very small error bar. And we could put this in the avalanche, but I think that is really a very important, becomes a much more important point as far as I'm concerned. Z evolution, that's, you heard what I just said. Of course, London CDM is doing very well there. And then in my personal avalanche is that the effect that we solve the riddle of the dark matter in dwarfs and that they are on the fundamental plane is fine. The missing baryonic matter. My last takeaway messages is we do know dark matter now better than baryonic matter. We have to find a workable prior for discriminating EG and MOND. We need to predict the Z evolution between Z0 and 2 in order to make progress with respect to the observation. And, but still, what Z black matter will be a big challenge. Thank you.
Thank you.
So thank you very much for a beautiful talk. I agree with you that we know better the dark matter than baryonic. So since you talk about the cool H2, in fact we have a way to correct a little bit the RR for cool molecular hydrogen.
Yes.
We have a way to correct, in fact, because it's proportional to the H1 gas. We have the tracer of this, the atomic gas. So have you in your sample enough dwarfs where they are dominated by gas, with atomic gas, and then we know that there is a factor 3 or 5 to multiply to have the molecular hydrogen, and then you could know exactly which kind of effect it does on the RER. If
So
you have it.
you're based on the, where do you base the, so you have to convert from one...
No, you know that the molecular hydrogen in general is 3 or 5 times more than the atomic in this kind of...
Yes.
So you could have this factor and correct the RER in this way and see what effect it can have. Do you have enough atomic hydrogen in your sample?
Okay. So,
Or have you tried to do this
where do you
correction?
get the conversion from? Normally people use the CO, right? For the
Yes,
conversion to
but in
molecular.
general you don't see the CO, but you have the atomic hydrogen.
Yes, but you have to convert from atomic to
Yes,
molecular.
exactly.
And that's a value, and how
Well,
do you get the value?
Yeah, we did some work some time ago, years ago,
Okay, yeah.
that we tried to have an idea of that, and it was a
Okay.
factor 3 or 5 more.
Okay, okay,
But there was also work by Hoekstra, I think, doing the same kind of thing.
okay. But we still, you agree, we still have an apparatus to
Exactly.
measure it.
Exactly.
So one thing to Francoise, so these are galaxies that you studied in the Big cleansing are relatively massive, right? They are massive, on the massive end of galaxies.
The largest are 10 to 11.
No, yeah, so aren't they expected to have sort of less gas in them, less neutron gas molecules and so on? So, no, certainly the ellipticals, it's not an issue there, right? No, just as a comment, which I didn't think about before.
I didn't mention it, but we included the cool gas in the files.
Yeah, but it might not be so important to add the molecules in these cases.
No,
okay, the one question I did want to ask about the contribution of hot gas to your analysis, when you said that you can actually eliminate the difference between early and late time. So is it the case, at least, that the gas starts to be, the hot gas starts to be important only at large radii? Let's say inside, at least there are several examples that I know where the gas was mapped, I think NGC 720 and another example, and the gas mass stars becomes equal to the sort stellar gas only beyond, let's say, 100 kiloparsec, 200 kiloparsec? Is this the general case?
Well, we don't know exactly yet.
Well, but in cases where there is...
of course, normally the assumption is, and the observation is that there's a high distance.
Yeah, but I understand, but they are much more extended in a way that if you plot the gas mass and the stellar mass as a function of radius, then stellar mass dominates up to about, let's say, 100 kiloparsecs, and gas mass starts to be important. So the gas mass will only enter your weak lensing analysis, which is beyond like 100 kiloparsecs, but will not affect, for example, RAR analysis with,
But know that, our observations, the weak lensing start at 50. The 30 kiloparsec is already a point which we hardly mentioned.
So it starts, that's what I'm saying.
50 kiloparsec, our measurements start beyond 50 kiloparsec.
Right. The other thing that there was a slight difference between MOND and in the theory at the high acceleration end of the round, if I remember correctly. I don't know how significant it is, but at least we know that we extrapolate into the solar system that it predicts anomalies that are much higher than what are observed. So they start to deviate from each other even at high acceleration. Can you show your...
I'm not sure which one you...
Okay, the one that's up. Right. So entropic gravity is the dashed line, right? And at high acceleration, we see that it goes above the MOND prediction and above somewhat. So I don't know how significant this is, but there is potential of discriminating also at high accelerations.
To be honest, we never paid much attention to this. But
maybe rightfully, but at least it's a point to remember.
I had a question very closely related to what Modi just asked about the X-ray. So for individual early-type galaxies that have bright X-ray halos, we have shown that they are actually on the same RAR as late-type galaxies, at least up to 10 to the minus 12 meters to square second. So it would be very strange if they start to deviate after that for whatever reason. And we've also demonstrated the same.
How is your work from what you have observations?
So early-type galaxies that have bright X-rays halos, spatially resolved information, so you can use the electrostatic equilibrium to measure the centripetal acceleration, and they are on the same RAR than late-type galaxies. And another example of early-type galaxies that are on the same RAR are lenticulars that happen to have very extended H1 disks, actually H1 rings in the other parts. They're also on the same RAR as spirals. So I mean, I think it's very likely that in the very other parts one is unaccounting for some Brouwer component, because in the more high acceleration region they are just behaving as late-type galaxies. So my question is actually, you made the point of the odd gas, which I agree, but another complication.
I go here because the echo is behind my ears. I don't hear anything.
The question is arriving now.
Okay.
Okay.
No, you tell me. Yeah, you tell me. And if I miss a few words, I give the wrong answer.
So the question is, I appreciate the point that in this figure at very low acceleration, you may be not accounting for all the variance, and so the hot gas component. But another complication are the mass-to-light ratios, which are different for late-type and early-type galaxies. And in individual galaxies, we have the near-infrared photometry for Spitzer, so that's very well under control. So I was wondering how much that could be an effect in a statistical sense in the kids' data.
Yeah, that's the number of 0.2 decks which is on our graph. So this is the MO ratio. It's actually the kids value, right? So this is done by the kids consortium, and so this is the actually they have been tuned also to the gamma observations because of the overlap with the gamma survey, the spectroscopic redshift, and spectroscopy. So there was a reference in one of my slides how that has been done. So, yeah, I'm not sure what the question is, but
so the question is whether, a small tweak of the mass to light ratios of early type galaxies could fix the issue.
well, that's, as I said, then you need to make an error of 0.4 decks, which is huge. 0.4 decks. That's huge. So our error is on mass to light ratio has a in my graphs has a area of 0.2 decks.
Factor of 2.
No, even more than the error.
You said that if you have gas, the same amount, then they come.
That's a good way of saying it, actually.
So, yes, which 100 both of those things.
So we have discussed the uncertainties resulting from the unknown mass-to-light ratio from the circumgalactic medium, but I wonder whether the contribution of the cosmic filaments is important for your measurements. We know, at least from in the standard model of cosmology, that the majority of barons in the universe are in the cosmic filaments. So what do you think is the contribution of the filaments to the signal that you measure?
Galaxies, stars, yes, I'm not sure what you're saying. Because we have been very strict on our isolation criteria, more or less the whole thing will be useless.
Yes,
So,
yes, yes,
so
but
the
galaxies
isolation
are...
criterion is no...
Yes, the cosmic web. So galaxies are connected with each other by cosmic web. There are filaments of intergalactic medium in cosmological simulations.
Sure.
In lambda CDM, there are filaments of dark matter, and this matter contributes to the total mass budget to each galaxy at very large radii. And here you measure the gravitational acceleration to very low values. This means that you are reaching very large radii where the contribution of matter in cosmic filaments might be important. So, and I wonder whether it really is important or not, or what do you think is the contribution of the mass in the cosmic filaments?
I'm not sure what to answer. So,
I think if you estimate the average acceleration field in the universe due to large-scale structure, it comes out to be a few percent of A0. So you're not really, you're just about reaching there. Certainly not within what galaxies are.
So, but anyway, on the filaments, so that should not act differently on ellipticals than on spirals. So, any systematic effects on the ellipticals and spirals, the one I know is MOND40, and that's more than it.
But for example, the geometry of the cosmic web might be different for elliptical and like type galaxies. The elliptical galaxies generally are thought to be in the intersections in large nodes of cosmic filaments, while these spirals are maybe just one or two filaments intersecting there.
Is EG supposed to be an alternative to MOND, or does it form a basis for MOND phenomenology?
Well, Eric did a fantastic presentation yesterday where he explained very carefully what is the overlap with MOND and what is the difference with MOND. So I'm not going there.
Well, yeah. What does MOND do? What does EG do with rotation curves? Because MOND predicts rotation curves, 100, 200 rotation curves, with considerable precision far out. What does EG do with rotation curves?
What is the question? So
Does it predict rotation curves? EG. What does it predict with respect to rotation curves?
it predicts the dark matter in
not in these galaxies. You can ask.
So you're talking about Stacy's result? Or what I'm not sure.
It's rotation. I mean,
Yeah.
since the 1980s, MOND has been reproducing with precision
Yeah.
galaxy rotation curves.
Yes,
And this simple little formula
yes,
predicts the rotation curves. Now with infrared photometry, without any pre-parameters.
Yeah.
What does EG do with rotation curves?
No, the point is that
it's the line which you'll go ahead.
it's
Oh my
not,
God.
it's not developed enough. It works only for spherical case, for example, and so on. So you cannot actually use it to predict it. It's just assuming that the galaxies are spherical. It's not.
So there's no predictive power in that scale for the theory.
But for elliptical,
First of all, the EG is divided for pointers, right? So what we do is we integrate over circles, and whether that is on spiral or elliptical, I don't see your problem.
no,
So
your
the EG is formally for pointers,
yes.
right?
This is
So,
a set of
and
observations.
clearly,
Rotational velocity function
let
radius.
me know.
And MOND predicts it. What does EG do with it?
I tell you that EG is formulated for a pointers, and certainly if you would make the case, really, I want an EG which is modeled, is derived for an extended mass, I'm with you. But the best we can do is integrating over the circles as we did in the
It's fine for
But both of these statements are correct, right? EG is formulated for a point mass. And so it doesn't actually predict, like MOND, in where the galaxy is finite, right? You need to do all of the usual Newtonian things there to get the MOND answer, and EG does not yet provide a mechanism by which you can calculate that right. So what Federico did do was make the spherical cow approximation, right? And when you do that, so in the very low acceleration regime, they go to the same thing, so they give you the same answer way far out. But in where the rotation curve still has a shape, they do not. And there's an extra force that comes in. Yeah, MOND gets it right and EG does not, unless you turn the mass to light ratio down. But that's for the spherical cow acceleration. I'm still not aware of a solution for a cylindrical disk.
As a matter of fact, but my presentation was on radii beyond 50 kilopascal. Yes, so that's it.
Within the vast range of phenomena.
No, you make this
it's not
map- you
approached
make-
by EG.
So I'm a bit switching topics. So I wanted to ask, precisely in these plots on the radial acceleration relation for the Fornax dwarfs. So these dwarfs are in a very strong external field. And so did you look at any possible correlation of the scatter in these points with, for example, the distance from the center of the cluster to look if there was any
Oh,
sign
we have a
of
lot of
this?
things on colors and stuff, a lot of papers on that. Not for this particular article.
So, in one of your plots, you propose 2 or 3 models which deviate slightly from the RAR. There is a relation that goes slightly below the RAR, and you had data points like falling in that region. But the error bars of these data points are so large. How do you show whether they are falling on the below relation, or the above relation? How do you if the error bars are large on the measurements, then how do you?
Not sure what you're talking about.
I can see the plot. Sorry.
So
Not this.
let me see.
Yes.
Do you want this one?
Yes.
This is the one with the air bars.
Yes. So do you think at least the points that are slightly below the RAR, if the error bars are better constrained, could you see a deviation? Or do you think it's possible to see deviation of?
So let me explain again. The blue error bars are from the gamma survey,
Okay.
which is 180 square degrees, and the black points are from the large survey, which is 1,000 square degrees. So we use the blue points just as a reference for consistency, because the blue points are the spectroscopic redshifts, while the black ones have photometric redshifts. So we use them, we compare them in order to see, you know, if you have all spectroscopic redshifts over the place, do it match? Does it match? So the final error bars are the black points here, which are amazingly small. Actually, they're measured on the diagonal of the covariance matrix. So they are major error bars.
Okay.
Hi, can you go back to the lambda CDM prediction, please?
I have no idea what it is. Let me see.
The Bahamas? No.
Was it here?
No.
It's here, yeah.
Yes. So if you look at the predicted signal you'd expect from an isolated NFW halo, it deviates massively below the RAR. So where do you think the extra lensing signal from both Bahamas and mice is coming from to boost it from what you'd expect from the NFW halo for mice, basically the same as MOND?
So what's the question?
So if you assume an isolated NFW halo, then it would deviate from the galaxy RAR much earlier than the Bahamas would, and it would go to much lower observed acceleration. It would be basically much below where the data is. So where's the extra lensing signal coming from in the simulations to basically match the MOND prediction for mice?
This is what is being measured.
Pardon?
No, this is what's being measured in the simulations. So the simulation will be done, and then the final cube, which is the result of the simulations, have been used to measure what, to determine what is the VAR of this set of data.
So if the lensing isn't coming from the NFW halo, surely it must be coming from some other structure or something.
The question is the simulations, why is there so much lensing at low acceleration?
Especially in the mice case.
Yeah, because an NFW halo doesn't give that much lensing.
Say that the one is similar to mice of Fornax.
Oh, that's, these are questions I cannot answer. I cannot answer. Sorry.
Well, an important thing to notice here is that neither Bahamas nor mice are demonstrated to explain the high acceleration in the distribution. I bet you anything they do not. That is, you extrapolate.
That's how you get the shape.
Yeah. So you can like I said in my talk, you modulate where the turnoff goes, right? So the shape of the Bahamas is correct for NFW. If you just, as others have already said, if you just calculate the lensing for one NFW halo, it's below either of those. Right? And so they're going to miss the high acceleration impact. You can already see Bahamas is turning away from that where it stops. It's really tragically low. The difference, if I understood what was said in the paper right, between mice and Bahamas is that when you select isolated samples from the simulation for the MONDs, there's a difference between Bahamas giving more or less typical halos, whereas mice was giving halos that were high concentration at the same mass for the same selection criteria. Now why that's different, I don't know, but that's why there's a difference.
Yeah, well, Carol notes in this paper, it's on my slides that you know. If you fiddle with the the halo to mass ratios in isolated galaxies versus non-isolated galaxies, you can solve the riddle, but yeah, that's right. Okay. I think the main conclusion I draw there is it is possible to produce a RAR, but it is not possible to use the simulations as a discriminator between what and what. So.
Okay, so thank you very much again.